Morning. Okay. Good morning, everyone. Give me a minute, please. Good morning, everyone. Gate people need to attend the flow measurement. No need to attend the flow measurement. Yes. So, okay. So we have been discussed about here. Yeah. So in yesterday's class, we discussed about the surges, and I have given you the question also. And we know how we have been determined this. Yes. Okay. So now let's see what is happening. The last in the open channel flow. Whatever the last part in the open channel flow now. So now last part of the open channel flow. Wave patterns. Wave pattern by dropping a stone. By dropping a stone in a flow or river or stream. So how the wave patterns are going to be there? See, there are a different type of flows we have been seen in the open channel flow: subcritical flow, supercritical flow, and critical flow. Now, if these type of flows are going to be there, then what happens to the wave pattern? How the waves are going to be changes? Okay. So the pattern that the waves are going to be followed when you drop a stone in a flow of a river. Now, let's see that. A. Give me a minute, please. Okay. Now, let's see. So what happens when you drop a stone in a flow of a river? And based upon this, we can say whether the flow is going to be subcritical or supercritical. Okay. Now, once we know the celerity concept, I said you the celerity means critical velocity of the wave. Yes or no? I have been discussed about the celerity concept. So, from here, the celerity means a relative velocity of the surge wave with initial flow velocity. And you know that in the case of the celerity means for a given flow, celerity of wave is nothing but a critical velocity of flow. Okay. Now, why I am doing this is when you drop a stone into a pond, then definitely you're going to see the yeah. So then definitely you're going to see some portion of the flow will be having some waves, right? Now, how those waves are going to be traveled? How those waves are going to be traveled? Yes. So now, first, if I drop a stone in a pond, means still water. What is the meaning of still water? Its velocity of flow is going to be zero. Its velocity of flow is going to be zero. Let's see. In the top view, there is a top view, my dear. Now, this is the flow, but what is the initial velocity of the flow? Zero. The velocity of flow is going to be zero. Okay. Now I am going to drop a stone. So now if I drop a stone, over here, so I'm going to drop a stone over here, and this is a axis of the axis where I have dropped the stone. Okay. So now this is where I have dropped a stone. Now if I drop a stone over here, what happens to the waves? See, when you drop a stone into a flow of river or a pond, definitely you can see the waves. Yes or no? And some of the waves will travel towards upstream. Some of the waves will travel towards the upstream. Some of the wave will travel towards the downstream. Yes or no? And whatever the waves they are going to be travel, it must be having some velocity VW. It must be having some velocity VW. Okay. So when I drop a stone, some waves are going to be developed, and that wave, you know what is the meaning of VW? Velocity of wave. And those waves has some velocity on upstream side and the downstream side. Now, if you know that, then what is the celerity, please? What is the celerity? Here, on the upstream side, what is celerity? On the upstream side, what is mean by celerity? Celerity means a relative velocity with respect to, what is celerity? Relative velocity of the surge wave with respect to initial flow velocity. Now, when the surge is traveling towards upstream, okay. When the surge is traveling towards upstream, see, these both are moving in different direction or not. When both are moving in different direction, then the relative velocity is going to be VW plus V1. But here, the relative velocity is going to be VW minus V1 because both are moving in the same direction. And you know that whatever the velocity at the critical flow, and that critical velocity is nothing but celerity. Yes or no? Now, please observe. So what I do is I'll keep V1 as 0. If I keep V1 as 0, now what is velocity of wave with which it is going to be travel? The velocity of wave with which it is going to be travel is celerity. The velocity of wave with which it is going to be travel is celerity. See, and that celerity is nothing but critical velocity or not? Yes or no? So Keep that in your mind, my dear. When you drop a stone in a pond where the initial velocity is 0, still water, now some waves will move towards the downstream, some waves will move towards the upstream. So in both the cases, the wave must be having some velocity dw, and in the case of still water, that velocity is same on downstream and upstream. And Baba, if the waves are going to be moving with the same velocity on upstream and downstream, then those waves are going to be symmetrical waves or unsymmetrical waves. Those are going to be the symmetrical waves. So now if I draw the wave pattern, those waves are going to be the symmetrical waves. So those are going to be the symmetrical waves. Now, whatever the wave pattern here, when you drop a stone into a still water, the waves developed are symmetrical to each other. So this pattern is going to be symmetrical wave pattern. Can I say it as a symmetrical wave pattern? And waves moves on both sides. So when you drop a stone, why? See, if you if you're observing a still water, if you drop a stone or if you keep some obstruction, you can see the ripples, and that ripples is going to be same everywhere on all the sides in still water. Why? Because when you keep that stone, then the waves are going to move with the celerity, velocity in all the directions. So that's the reason why it gets a symmetrical wave pattern. Okay. So if V1 is 0, then how is it moving in downwards? Remember, V1 is 0 means generally I am taking the flow pattern. Why I am taking V1 is 0 means let's say it is a still water. Okay. Generally I am taking this one as upstream and this one as a downstream. Now let's see if it is a subcritical flow. What is the meaning of subcritical flow? What is the meaning of subcritical flow? The meaning of subcritical flow is, you know that the meaning of subcritical flow means a flow with a lesser velocity, or the velocity of the flow is going to be less than the critical velocity, right? So the velocity of flow is less than critical velocity. And what is that critical velocity? Critical velocity is nothing but C, right? The critical velocity is nothing but C, means celerity. Yes. Again, this is a river. Now, in this case, the V1. Now this time, this is the axis of dropping of a stone. This is the axis of a dropping of a stone. Now this time the velocity V1 is not going to be 0. V1 is greater than 0. Now V1 is greater than 0. Generally the flow is happening like this. Generally, let me say the flow is coming like this from upstream to downstream side. Now I am dropping a stone over here. So when I drop a stone over here, now come on, tell me. Now I'm dropping a stone over here. So if I drop a stone over here, now what is going to be happen? Tell me. Same. These waves will move with some VW and both VW would be there. Yes. Now let's see what is that celerity. See, celerity is going to be same equation. The equation of the celerity is here. VW plus V1. Here VW minus V1. But in the earlier case, in still water, V1 is going to be 0. But here V1 is greater than 0. So now you tell me the VW here is C minus V1. Here VW is C plus V1. So now, my dear students, can you please tell me in which side does the velocity of the wave is more? This is upstream side and here it is going to be downstream side. In which side the velocity of waves are going to be more? Tell me. On the downstream side the velocity is more or upstream side the velocity is more? And why C, sir? What is C? The C is nothing but critical velocity or not? Yes or no? The C is nothing but critical velocity. So in this case, can I write the velocity of wave is less than C? And in this case, velocity of wave is going to be greater than C. Yes or no? So in the case of the downstream, the velocity of wave is going to be more. And in the case of the upstream, the velocity of wave is less. So now when I drop a stone, on downstream side more velocity, on the upstream side less velocity, which means more waves will travel towards the downstream than the upstream. Now, is it a symmetrical wave pattern or unsymmetrical wave pattern? Now, if I draw the wave pattern over here, so now let's see. You can observe more waves will travel towards the downstream. More waves will travel towards the downstream. So I can write in subcritical flow, by dropping a stone, waves moves in both directions unsymmetrically or symmetrically? Unsymmetrically. With more on downstream side. So this is an unsymmetrical wave pattern. Okay. So I can say this is unsymmetrical wave pattern. Now, if you see this is a subcritical flow, then let's see. I am increasing the velocity of flow. Earlier, I take the still water and then the subcritical flow. Now let's see the supercritical flow. Critical flow. What is the meaning of critical flow? Critical flow means whatever the velocity is nothing but critical velocity is nothing but celerity. Whatever the velocity is nothing but the critical velocity, and you know that critical velocity is nothing but the celerity, right? We do know that critical velocity is nothing but the celerity. Now let's draw the same thing. Okay. So same. Now I'm going to represent the axis where I'm going to drop a stone. Axis where I'm going to drop a stone. This is the axis, and this is the point where I'm dropping a stone. But this time, the velocity, the flow is moving with the critical velocity. The flow is moving with the critical velocity. Then when I drop a stone, what happens to the velocity of the surge wave? Velocity of the surge wave. So here, celerity means VW minus V1 plus V1. Here, celerity means VW minus V1. Now, I want VW. What is VW? What is VW? VW means V1 minus C. Yes, sir. And what is V1, my dear? What is V1 in the critical flow? In the case of the critical flow, V1 is nothing but Vc and Vc is nothing but C. C minus C, then 0. And what about here? VW is this is C minus V1. So this is C plus V1, C plus C, which is going to be 2C. Yes or no? So now you tell me, in the case of the critical flow, when you drop a stone on the upstream side, is there any wave pattern? On the upstream side, what is the velocity of the wave? 0. And on the downstream side, what is the velocity of the wave? 2C. Yes or no? The velocity of wave is going to be 2C. You can see over here. On the upstream side, velocity of wave is 0. On the downstream side, velocity of wave is going to be 2C. Now you tell me, do you think any wave will travel towards upstream? No. No wave will travel towards the upstream. No wave will travel towards the upstream. Okay. And every wave will travel towards the downstream only. Let's see. You see, all the waves are traveling towards whom? Downstream or upstream? Every wave is traveling towards the downstream, and all these waves are going to be tangential to the point of a dropping of the stone. All the waves are going to be generated as a tangential to the point of dropping of the stone. So now I can write a point over here as, by dropping a stone, in river or in critical flow, waves travel towards downstream side. Waves travel towards downstream side, and wave pattern is tangential to point of dropping of stone. And the wave pattern is going to be tangential to point of the dropping of the stone. This is nothing but a tangent, my dear. This is a tangent tangential to the point of dropping of the stone in the case of the critical flow. So I hope you understood what is happening. So as the velocity of the flow is going to be increases, as the velocity of the flow is going to be increases, the wave pattern is going to be moving more towards the downstream side. So yes, practically it is possible. Practically it is not possible, sir. Why we study this topic? Why we study means to make sure what is going to be happen in reality. In reality, when the flow is going to be there, if you want to predict the type of flow, whether it is subcritical or critical or supercritical, then you can simply, the flow is happening, I'll keep a pen over there, it will cause some disturbance, then the waves are going to be travel on. Wait a moment, then I can say that for you. Now, the last one is a supercritical flow. If it is a supercritical flow, then what is going to be happening? If it is a supercritical flow, in the case of the supercritical flow, the velocity V1 is greater than the critical velocity, and you know the critical velocity is nothing but the celerity. V1 is greater than the critical velocity. Now, we study this topic to know how the waves are going to be travel, and based upon the waves, I can directly state the type of flow. Now, there is a point I am dropping a stone. This time V1 and V1, celerity VW plus V1, celerity VW minus V1. Now here VW is nothing but C minus V1, and V1 is going to be more than C or not? Yes or no? So then this VW is going to be less than 0. And similarly here VW is a C plus V1, and what is V1? V1 is greater than C or not? V1 is greater than C. So VW is more than 2C. Because what is V1 value? What is V1? V1 is more than Vc, which means V1 is greater than the celerity. V1 is greater than the celerity. So C plus greater than celerity 2C, C minus less than greater than celerity less than C. See, the meaning of that one is, whenever the velocity is going to be 2C, then all the waves are going to be start at one point. All the waves are going to be start at one point, and all the waves are going to be tangential to the point at which the flow is going to be drop. The stone is going to be dropped. But in this case, the waves will sweep more towards the downstream side. The waves will sweep more towards the downstream side in increasing the wave pattern. Now see. In increasing wave pattern, and it just looks like a cone. The wave pattern is going to be a conical wave pattern. So this type of wave pattern is going to be the conical wave pattern, conical waveform. So in the case of the supercritical flow, if I drop a stone, the waves are going to be moves entirely towards the downstream side, and with increasing the wave magnitude, or wave sizes, okay. By dropping a stone, in supercritical flow stream, waves sweeps more towards downstream as a conical wave pattern, from the point as a conical wave pattern. So these are the things that when you drop a stone, what happens to the wave patterns? So generally we used to throw a stone in such a way that it bounces on water with velocity. Is there any condition in our topic? No. Arey, wow, it's not a vertical here. It's, see, I am showing you the plan view, my dear. This is a plan view. The axis is not vertical. See, whatever the dropping point there with respect to that. Okay, now let me show that some videos for you. Okay. Yes, now let's see that. You can observe, see whatever I'm showing you here, whatever I'm showing you here, this is nothing but a hydraulic jump, right? So where the supercritical flow is meeting the subcritical flow. Now everybody have a look what is going to be happen. Now I'm showing you, now, see in the case of the subcritical flow, what is going to be happen? See here the waves are going to be travel in such a way. So now more waves, if this is a subcritical depth. Yeah. If it is a subcritical depth. Now if I keep a broom or a stick, see now I am inserting some broom or a stick. So this is a broom or a stick. Now this is the point where I am going to insert. Now let's see what is going to happen. Observe. So when I keep that, then again observe. So you can see the wave pattern or not? You can see the wave pattern, how the wave is going to be flows. Yes or no? But in the, this is subcritical flow, because the subcritical flow means that depth is more, velocity is less. You can see the waves are going to be, see the flow is also moving very slowly. Yes or no? Now when I insert here, the flow is passing in this direction. The flow is passing in this direction. This is an upstream. So the flow is passing in this direction here. So now you can see more waves are going to be traveled towards the upstream side. So more waves will travel towards the downstream side. Now let's see. Yeah. So more waves are traveling towards this side, right? So I'm saying this flow, more waves are going to be travel and less on the upstream. You can see the wave pattern over here. You can see the wave pattern. Now, similarly, in the case of the supercritical flow, how is it going to be seen? In the supercritical flow, subcritical flow, yes, I hope you can understand. Now, you see, in the case of the supercritical flow, the flow is already moving. The flow is already moving from upstream to the downstream side. Okay. Now I'm keeping or inserting a broom over here. If I insert a broom over here or a stone over here, now you observe what is going to be happen. Here is supercritical flow. Now you can see there is no wave is moving towards the upstream. There is no wave is moving towards the upstream. Entire waves are going to be moved towards the downstream. Yes. No wave is moving towards the upstream. Entire waves are going to be moved towards the downstream only. So now if you see here, the waves are going to be moved as this is known as a conical wavefront. This is known as conical wavefront. So in the case of the supercritical flow, when you keep an obstruction or a flume or any broom or any stone, what happens is the waves will travel towards the downstream side. Now, yes. So if you see in subcritical flow, lesser flows will travel towards upstream and more flows will travel towards the downstream. And in the supercritical flow, every wave is going to be traveling towards the downstream. And what is the wave pattern over here? And this wave pattern is nothing but a A conical wave pattern. There is a conical wave pattern. So by keeping a stone or a broom, you can see this one. These are different type of flows. So you can see a lot of videos in the case of the in YouTube. If you go, there are a lot of videos, but I am showing you a few videos only because with the time permitted for us. But whenever the time is there for you, you please go through those videos. Okay, I hope. Yeah, I hope you understood this. So now that's all with the open channel flow. And yes, a lot of people are asking that there is a flow measurement in open channel. See, the flow measurement in open channels is different. The flow measuring devices is different. For the IES, there is an exclusive topic known as a flow measuring devices. Viers, notches, barrages, viers, notches, mouthpieces, orifices, and all those things. That's for IES, it is different. Okay. And for the gate point of view, that's different. That's only small topic that is known as a broad crusted weir, critical flow measurements, that I'll be discussing once I complete the dimension analysis also. Once I complete the dimension analysis, I'm going to discuss that. Just some 20 to 30 minutes topic, that flow measurement in open channels is different. In the pipes is different. But for the IES students, we are going to discuss about total flow measuring devices total in the case of the separate chapter. But for the gate people, I'll be discussing only small topic known as a broad crusted weir. What is that? We'll be seeing later. So that's all with the open channel flow. With this, we completed the open channel flow full. So there is no leftover topics in the open channel flow except that flow measuring, that too broad crusted weir only, that I'll be saying at the end of the dimension analysis. So now, can I leave? There is no hydraulic machine, sir. What about unsteady RVF? Are Baba, what is mean by surge? Where are you? Are you in the class or not? The unsteady RVF is nothing but the surge, my dear. So when will you take a lateral loads on piles? See, and geotechnical engineering, the people who have already attended the geotechnical engineering, so you know that in geotech, this year they have added one more topic in pile foundations. So lateral loads. And that topic we'll be discussing based upon, because by the time I have taken the batch students, and this time some more additional batch students were there. So whatever the batch I have taken earlier, for that I have to take a separate slot of at least a half an hour. So I'll be let you know by today, because I have to discuss with the team, schedule team. So based upon that, I can say you, and I'll be let you know that tomorrow. Okay, today by the end of the session, I'll be let you know. Okay, now let's come to the next topic. Yeah, there is a chances of increasing the weightage for the FM2 as they have removed the hydraulic machines. So, okay, yesterday I have given some homework problem, right? Yes, this homework problem, I hope you might have done this question. I have asked you this question as a homework question. Let's see that question, please. Okay. In a rectangular channel of depth 1.2 meters, in a rectangular channel of depth 1.2 meters, and velocity 2 meter per second, and velocity 2 meter per second. Okay. So now an elementary wave traveling upstream, you see, they have given the depth 1.2 meters, velocity v1 as 2 meters per second. An elementary wave is traveling upstream with a velocity, will have an absolute velocity. So if the elementary wave is traveling towards the upstream, generally the flow is going to be towards downstream. Then what is the celerity for this? The celerity is VW plus V1, because they're opposite in the direction, right? Is equals to. Now, you know that this is celerity. Did I mention anything regarding to the small surge or large surge? No. I told you when they don't mention anything, you always go with the small surge. Because you don't know the depth, right? You don't know what happened due to that surge. Does the depth has been doubled or increased or decreased? We don't know that. So now, you see, I want VW plus 2 is equals to root of 9.81 into 1.2. What is this VW, please? Minus 2. The answer is going to be 1.43 meter per second. So that's about the question. Now, let's see the next topics. I hope you understood this. Okay. Next, the new topic dimensional analysis. So dimensional analysis. Now, in the case of the dimensional analysis, now let's see. So here, what is meant by dimensional analysis? Why we are going to discuss about that? See, this is not about only the open channel flow. This is about the pipe flow, and this is about the civil engineering. What we are going to discuss here. So coming to the dimensional analysis, what is meant by dimensional analysis? The first definition of the dimensional analysis is it's a mathematical technique. It is a mathematical technique. Okay, why we are going to use the dimensional analysis means why we are going to name it as a dimensional analysis is we are going to analyze the name of dimensional analysis. As a layman, we are going to analyze any civil engineering problem or any engineering problem, let's say, because we can use this dimensional analysis for all the engineering. So any engineering problem, we are going to analyze by studying the dimensions of the object you are going to take, whether it's a fluid dimensions, if it's a solid dimensions. Okay, so whatever the system you are going to analyze means for the engineering problem, to analyze the engineering problem by studying the dimensions of that system is known as a dimensional analysis. So it's a mathematical technique. Sir, why we need to study this dimensional analysis, sir? Because see, whatever the systems we are going to discuss so far, for everything there must be some system. For example, you take a continuity equation. You take a continuity equation where we are going to apply the continuity equation. Wherever there is a flow, there we are applying the continuity equation. Wherever there is a flow rate means mass, then definitely A1 V1 is equals to A2 V2 is equals to so on. So that's nothing but a fluid flow. And in that, we are applying the dimensions by studying their dimensions, And how we are going to study the dimensions, sir? By means of physical or fundamental dimensions with respect to mass as m, dimension, length parameters, all the length parameters like channel geometry. If you take a channel geometry, you see, I'm going to give the open channel. You know the channel geometry, length, top width is in length in terms of meter, depth of flow in terms of meter, weighted perimeter is in terms of meter, hydraulic radius in meters, hydraulic depth in meters, cross-section area is in meter square, volume meter cube. So whatever the terms that relate with the geometry, that is going to be represented with L square, L cube and everything. And whatever the parameters are that represents with the fluid property, like forces, whatever the forces we are going to discuss, surface tension, viscosity, all are going to be represented with the mass. And whatever the kinematics means when the flow is going to be happen, it is going to be moved with some velocity, acceleration, discharge means a flow rate, and angular velocity, all those things are going to be represented with the time. So basically, whatever the system I give to you, especially we use this dimension analysis for the fluid flow. When a flow is happening, then that flow will happen through one medium. If it is a pipe flow. If it is an open channel flow. And for that medium, there must be some cross-sectional details, and those are represented with the channel geometry, means geometrical variables. And number 2, and when the flow is passing, it is having some kinematics, means with respect to time, acceleration, velocity, flow rate. That's with respect to time, dimension as time. And that flow will be having some property like forces, viscosities, surface tensions, and that are represented with the mass. So basically, we deal and we study all the engineering problems by a 3 fundamental dimensions or units known as M, L, T. By taking these 3, we are going to solve the engineering problems. So definition. What's the definition? It is a mathematical technique So dimension analysis is a mathematical technique to solve engineering problems. By studying fundamental dimensions of the system, Okay, now the primary or fundamental dimensions are mass, represented with the capital M, length, represented with the capital L, time, represented with the capital T. Okay, and if you go for the temperature in the mechanics, in the mechanical engineering, you have to look over the thermal also. So in the case of the mechanical engineering, what you need to do is you have to look over the temperature. So there the time, the small t represents the time and the capital T represents the temperature. And so wherever you require, in the case of the electrical engineering, so there you have to look over the electric current in terms of amperes I also. So but for our civil engineering problems, what we discuss is majorly M, L and T. So this is majorly the dimensional sensor are going to be a primary tool for analyze the fluid flow. This is a primary tool to analyze the fluid flow. Now let's see what is the usages of the or objectives of the dimensional analysis. What is the objectives of the dimensional analysis? Objectives of dimensional analysis or uses of the dimensional analysis. Okay. See, once I know the system means if I take for example, when a flow is happening, the flow rate is passing through the channel. So there is nothing but discharge Q. And how come I say Q is equals to A into V? How come I say Q is equals to A into V is by checking the dimensional homogeneity between the system. For example, if I take Q is equals to A into V, now what is the units of the Q over here, which is nothing but meter cube per second. What is the units of the area? Meter square. What is the units of the velocity? Meter per second. Yes or no? So now here meter cube per second, here also meter cube per second. Yes or no? Which means on LHS and RHS, the dimensions of the given system are same or not? And when they are same, then they are going to be homogeneously, means a dimensional homogeneous to each other. Dimensionally homogeneous to each other means whatever the quantities I have taken on the left and the right, both are having a same dimensions. If they are not having same dimensions, then they are going to be dimensionally non-homogeneous. Which means, for example, you take the Manning's equation. So what is the Manning's equation? V is equals to 1 by n into r to the power of 2/3 into s to the power of 1 by 2. So what is the units of the velocity? Meter per second. But does n has any units? No. Does s has any units? What is s? Slope, right? Slope has no units. And what about r? R means meter. Meter means meter to the whole to the power of 3 means L by T, and this is going to be L to the power of 2/3. This is L cube by T. Here it is going to be L cube by T because meters, right? Meter can be written in terms of the length and seconds can be written in terms of the time. So this is the primary dimension over here and this is the dimensions over here. Now, can you tell me which one is going to be dimensionally homogeneous? Which one is going to be dimensionally non-homogeneous? First one is dimensionally homogeneous because on the left side of the system and right side of the system, the dimensions are same. And if you see here, on the left side, the dimensions are different. Right side, the dimensions are different. So this is a dimensionally non-homogeneous. Homogeneous means LHS and RHS are same. Non-homogeneous means LHS and RHS are not going to be same. So if I know this dimensional analysis, if I know this system, then whatever the equation you give to me, I can say whether it is going to be homogeneous or non-homogeneous. So point number one, the simplest form is to check the dimensional homogeneity of the any equation in the fluid motion. You check any equation. So point number one, to check dimensional homogeneity of any equation in fluid flow. This is a number one. And number two is to reduce the number of variables. For example, I'll give you one question. I'll give you one question for you. So now you see when the flow is going to be happen, through a channel. Listen to me carefully. When a flow, so you know the channel, right? So when the flow is going to be happen through a channel, let's take this is some channel, rectangular channel. So this flow having some velocity, yes or no? So if I take a plan view, this is going to be the velocity of the flow. So now when I allow some flow to pass over some channel, then whatever the flow velocity passing through this channel, depends upon whom? The shape of the channel. Depends upon the shape of the channel. Because see, if I send the same flow rate 10 meter cube per second, if I send some flow rate of 10 meter cube per second, so do you think the velocity of flow will be same in rectangle and triangle? No. So depends upon the shape. The velocity depends upon the shape of the channel and the size of the channel. Yes or no? The velocity depends upon the size of the channel. The velocity depends upon the roughness of the channel. Yes or no? And the velocity depends upon the bed slope of the channel. Yes or no? So which means there are lots and lots of factors. So here the velocity depends upon the size, shape, slope, and channel irregularities and vegetation, scouring, silting, and see, these are all the various factors. Yes or no? What is the shape? What is the size? And what is the side slope? And what is the bed slope? What is the bed slope? So when the flow is happening through a channel, means I am discussing about open channel, that flow velocity depends upon what is the shape of the channel, size of the channel, side slope of the channel, bed slope of the channel, and for that a boundary would be there, and on the boundary what is the roughness, and when there is a transitions are there, when there are transitions you need to find out the transitions also, means channel bed irregularities, and at the bottom there must be some vegetation, so that vegetation also, and there must be some silting, there must be some scouring. There are lots and lots of factors are there for a given problem. So now my problem is the velocity of flow, and that velocity of flow depends upon various factors. Now this dimensional analysis will help us to reduce that total number of variables to a few variables only. Then we can analyze much more better. Sir, how, sir? Now you see what is the empirical equation of Manning's n, right? And this n, see how many relations are there in this? Velocity v is equals to 1 by n into r to the power of 2/3 into s to the power of 1 by 2. Yes or no? Okay. Now if you have this one, then simply in all the conditions this velocity n depends upon n, and n is a function of whom? All these things: channel irregularities, vegetation, scouring, and silting. And r is a function of whom? Shape, size, and side slope. This is going to be r. And yes, sir, this is going to be yes. See, you observe clearly, earlier there are a lot of factors. Now with the help of the dimensional analysis, what I made is I reduced all these factors to n, shape, size, side slope to r, bed slope to s. How many variables are there now? Only 3. Earlier how many? 1, 2, 3, 4, 5, 6, 7, 8. So earlier 8 parameters are there. 8 parameters or variables are there. Now I reduced that into only 3 as n, r, and s. So point number 2 is this dimensional analysis will reduce the number of variables and arranges them into a dimensionless parameters. arranges them into a dimensionless groups. Okay. So, hope you understood. Does dimensionless work covered in fluid mechanics for you? Okay, fine. If it was covered, then fine. But the way that I discuss is different. So we must have to go through that. No. So, so point number 2 is to reduce the number of variables in system by dimensionless groups. So by dimensionless groups. So how we are going to reduce it dimensionless groups and find out the analytical solution, we'll see it later. We'll see it later. First is dimensional group and all those things. That I'll take one example, and based upon that example, I'll explain that. Now, the next one is, so the last one, this is very important, known as model tests. For example, we are civil engineers. We want to construct a dam, or we want to construct a weir. Are you go to site directly, and are you going to construct the dam directly, and then you are going to allow the flow to the dam, and then are you going to check how the dam is going to be acting under the action of water? Are you going to construct the structure directly, and then you are going to analyze the behavior of that dam under the action of water? Or are we going to do the test in the laboratory first? We are going to do that test in the laboratory first. Means we construct or we made a small scale of that dam, and we test the dam in the laboratory. Yes or no? We test the dam in the laboratory, means we test how the dam is going to be takes, whether the dam is going to be failed by overturning or by sliding, or what are the forces acting on the dam. So are we going to analyze that dam in realistic conditions, or are we going to analyze the dam in the lab or experiment first? We do tests on the small scale of the actual dam, and based upon those tests, we can say what are the forces acting on the dam and how the dam is going to be resisting those forces. Based upon that only, we are going to design, and once we design, then we construct. Yes or no? So before constructing any engineering structure, whatever it is, whatever the development that you are going to see, so they, first of all, they have to test on the small scale models or not. That model is nothing but small scale replica of the actual prototype. You see, before sending a rocket or before going to the space, the astronauts has to prepare themselves. Yes. So where they are going to be do that themselves. So in the space stations, they create a small shuttles where it can create environment of the space. That's nothing but a model, and there they are going to be checked. Yes or no? Similarly, wherever you see, so first of all, you need to do some tests on a small scale replica of a model, and then we design for the actual. And that one, how we are going to do the test is based upon its dimensions again. See, if I want to construct a dam in the reality, are you going to do the experiment on the channel, or are you going to do the experiment on the dam? You're going to do the experiment on the dam itself, right? So now that is known as a model test. That is known as model test. To conduct model test. To conduct the model test and present the experimental results. experimental results. So our main aim is going to be to check the dimensional homogeneity and in the given system reduce the total number of variables into few number of variables as a dimensionless groups, and then before designing and the construction of actual structure known as prototype, we need to conduct a test on the models and we have to represent those experimental results. Okay. The model means the small scale. The model means a small scale replica of the actual structure. The actual structure means prototype. Remember, the actual structure is prototype. Whatever the construction we do, that is a prototype. And based upon that, we create a small scale one that is known as a model. So to conduct the model test and we are going to present the experimental results. So these are the objectives of the dimension analysis. Now let's see. Yes. Okay. Now let's say the first dimensional homogeneity. What is meant by dimensional homogeneity? So a system is said to be, or an equation is said to be dimensional homogeneous if the dimensions of the system, on both the sides, LHS and RHS, are going to be same. Okay, so that's what the dimensional homogeneity. So this is a basis of the dimensional homogeneity. This is the basis, means our base of dimensional analysis. And it was given by Fourier's, not 4 years. Fourier's dimensional homogeneity we said as a, so basis of the dimensional analysis. And when do you say the equation is going to be dimensional homogeneity? An equation is said to be dimensionally homogeneous. An equation is said to be dimensionally homogeneous if the dimensions of system are same on LHS and RHS. So if the dimensions of the system are going to be same on LHS and RHS, we call it as a dimensionally homogeneous. Example, all derived equations are dimensionally homogeneous. All derived equations are dimensionally homogeneous. And the examples are, just say, Q is equals to AV, F is equals to MA, and even Chezy's equation. The Chezy's equation is also going to be the derived equation only, right? So whatever, this is nothing but P is equals to rho GH. Yes. So these are all the derived equations. Momentum flux, M is equals to rho QV. So all are the derived equations. So for all these derived equations on LHS and RHS, the units are same. The dimensions are same. Now, if the dimensions are not same on both sides, If the dimensions are not same on both sides, then equation is said to be dimensionally non-homogeneous. Equation is said to be dimensionally non-homogeneous. So if the equation means if the dimensions are not going to be same on the both sides, then it's going to be dimensionally non-homogeneous, and all empirical relations are non-homogeneous. All the empirical relations are the non-homogeneous. Examples, so what we know, velocity 1 by n into r to the power of 2/3 into s to the power of 1 by 2. So in the irrigation, you are going to see Cutter's equation. In the irrigation, you are going to see the Cutter's equation. There are a lot of equations are there. So Kennedy's equation. These are all the empirical relations. Whatever I want to see, you don't know the remaining things of fluid mechanics and irrigation. So that's the reason why I'm going with whatever the discussion I made. So this is about the dimensional homogeneity. To check the dimensional homogeneity, just simply you look on the LHS and RHS units, and if both are same, then you say it as a dimensional homogeneity. If they're not same, non-dimensional homogeneity means dimensional non-homogeneity. Okay. So this is the first objective, and it's already 8:30, and let's have a small break, because whatever the next one, it will take a lot of time, because to reduce the number of variables into system by dimensionless groups, so it will take a lot of time, but once we start, it won't stop. Let's have a small break. Even I don't know, my throat is paining today. Let's have a small break of 15 minutes, and we'll resume our session after 15 minutes. So come by 8:45, it's 8:32. Okay, come by 8:50. We'll start our resume at 8:50. Have a break, please. Yeah. So let's come to the next methods of dimensional analysis. So methods of the dimensional analysis. What are the methods of the dimensional analysis? See, what is the meaning of these methods of dimensional analysis? Now, you see what is the objective of the DI I said you? The objectives of the DA is number 2, to reduce the number of variables in the system by dimensionless groups. So the methods of the dimensional analysis will help if the total number of variables are known in a group, then it will give you the relation between the variables by dimensionless groups. If total number of variables in system is known, relation between those variables can get by two methods, Rayleigh's method. Second one is Buckingham's pi theorem. Buckingham's pi theorem. Okay. So two methods. One is going to be Rayleigh's method, and other one is going to be Buckingham's pi theorem. So in the case of the C, whatever the system you take, if you know the total number of variables, then in that system, the relation between those variables can get by means of the Rayleigh's method and Buckingham's pi theorem. Okay, but in this, the Rayleigh's method is not useful because it cannot be useful if the number of variables are more than 3. If the number of variables are more than 3, then the Rayleigh's method cannot be useful, not useful much. So if the more number of variables are going to be locating in a given problem, if more number of variables are parameters, see, I'm using a term, so variables are parameters in a given system, then you must have to go for the Buckingham's pi theorem. And moreover that, here, in the Buckingham's pi theorem, the number of dimensionless groups will be known earlier. Dimensionless can get as dimensionless groups. Dimensionless are non-dimensional. The number of dimensionless groups will get to know earlier. Okay. So now coming to the Buckingham's pi theorem, what the Buckingham pi theorem says is, now according to the Buckingham's pi theorem, what he says is, if a dimensionally homogeneous system or equation has a total number of variables as n, if a dimensionless homogeneous equation, so you take any equation, if that equation consists of a dimensionally homogeneous equation, if that is, and if that equation consists of a total number of variables as n variables, total number of variables as n, small n variables, and the variables with the fundamental dimensions are 3. The variables with the fundamental dimensions are, so what are the variables with fundamental dimensions? M, L, T. So whatever the variables are that are having a fundamental dimensions as m. So if the total number of variables are n, according to the Buckingham's pi theorem, in a in a dimensional homogeneous equation, in a dimensional homogeneous equation, if there are n total variables are parameters. If there are total variables are parameters, which means dependent plus independent. So both dependent variables plus independent variables. Like for example, Q is equals to AV. Is it a dimensional homogeneous equation or not? Yes. Think, listen to me. I'm going to take one example, one big example. From that I can say, but as of now, you see. So let's take a Q is equals to AV. That Q is equals to AV means the flow rate passing through the channel or a medium depends upon area, the cross-section area means channel geometry or pipe geometry, and the velocity of the flow passing through it. Yes or no? So in the equation of Q is equals to AV, how many variables are there total? 1, 2, 3. So how many total number of variables are there? 3 variables are there. And who is dependent and who is independent? Who is dependent and who is independent? Who is dependent here? The discharge is going to be the dependent. And the area and velocity are independent. So in a dimensional homogeneous equation, if there are n number of total variables or parameters, so how many are here? 3, which consists of dependent plus independent. With m variables of primary or fundamental dimensions. Primary or fundamental dimensions. What are the primary or fundamental dimensions? M, L, T. See, keep that in your mind. Whatever this m variables are small m, not capital M. So if n total variables consists of m variables of primary or fundamental dimensions, then the variables arranged as n minus m is known as dimensionless groups, dimensionless terms. Then the variables are n minus m is known as a dimensionless terms, and these dimensionless terms is also known as a pi terms. What we call it is a pi terms. So why Buckingham's theorem is going to be the pi theorem is because in the case of the Buckingham pi theorem, the number of the dimensionless groups or terms will be known earlier. How, sir? By means of n minus m. Okay. But in the case of Rayleigh's method, you cannot know the number of the dimensionless groups earlier. You can find out the relation, but you cannot know the number, total number. But in the case of the Buckingham's pi theorem, that you can know directly here. So where n is total number of variables, m is also known as repeating variables. M is known as repeating variables, which means variables with dimensions MLT. Now, number of pi terms is represented with the n minus m. N minus m. So, okay, fine. Now, how I get the relation between these variables? How I get the relation between these variables? See, for getting the relation between the variables, first of all, you need to know how to select the repeating variable. See, I know the total number of variables, and now, first of all, we need to know how to get the repeating variables. Selection criteria of repeating variable. So selection criteria for the repeating variables. Point number one, whenever in the given system, whenever in the in the given system, let's take Q is equals to A into V. Let's take Q is equals to A into V. So how many total number of variables are there? 3. And in this is going to be the dependent and these are going to be the independent. Okay. So here Q is going to be the dependent and A and V are going to be the independent. Yes or no? So now you see in this case, point number one, the dependent variable should not be selected as a repeating variable. Means you should not take the Q as a repeating variable. You should not take Q as a repeating variable. So point number one, dependent variable should not select as a repeating variable. Okay. Now, point number two, repeating variable should be selected as one variable has geometry details, or geometry property, other has repeating variables. So how many are there? One variable has a channel geometry details, which means one variable should consist of geometry as a L. Other has kinematic property and another has fluid property. Okay, so keep that in your mind. Now while you are taking the repeating variable, so how many maximum number of repeating variables would be there is 3. Why, sir? What are the total number of primary dimensions we are dealing? 3. What are those? M, L, T. So while you are selecting the repeating variable, how you are going to select is, number one, whatever the number of variables I give to you, you don't take the Q as a repeating variable because this is nothing but dependent. Now coming to the A into V, what is the dimensions? First of all, you have to write down the dimensions of area. What are the dimensions of area? Meter per second square. Sorry, meter square. Meter square means L square. Meter square means L square. And velocity means meter per second, which means L by T. Okay. So now the maximum number of the repeating variables are 3. Out of that, one variable should consist of a geometry property. Other variables must consist of kinematic property, and another has a fluid property. Sir, what is that, sir? Now let's see. Geometric variables are length. See, don't worry. First, let me complete this. Then you can understand much more better. Length, width, area, volume, moment of inertia, etc. That comes as a geometric variables. That comes as a geometric variables. Then kinematic variables. What are the kinematic variables, sir? Kinematic variables means like velocity, acceleration, discharge, angular velocity, rotational velocity, etc. Means the term which related with the length is geometric variable. The term which related with the time is going to be kinematic variable, and next one is fluid property. Whatever the fluid property that deals with the mass, m. So fluid property, for every fluid it must be having some density. Every fluid must be having some density, some viscosity, surface tension, etc. So these are the properties: density, viscosity, compressibility, and surface tension. These are the properties of the fluid. These are the fluid properties that are depends with the mass. Okay, sir, fine. You are saying that, okay, point number one, dependent variable should not be selected as a repeating variable. And the repeating variable must consist of one variable has a geometry, kinematic, and fluid property. So then how we are going to select for this? The last point is very important point. This is point number one, point number two, and now the point number three is no two repeating variables has same dimensions. No two repeating variables has same primary dimension. This is very important. So what is the meaning of this one? What is the meaning of this one? Yes. Momentum is mass into velocity. Moment is not a property, okay? Yes. So now what is the meaning of this? No two repeating variables have same primary dimensions. Now let's see. Example, Q is equals to A into V. Q is a function of A and V. Q is a function of A and V. And A is a function of whom? A is a function of whom? Length. or dia or whatever the things. Yes or no? So now you see Q is equals to function of A into V. Now in this the total number of variables are, see this is a dependent and you know this is a dependent and these two are independent. Yes or no? So how many variables are there total? Total number of variables are 3. Now if I want to find out the dimensionless groups, if I want to find out the dimensionless groups, then I need to find out the m value. Yes or no? So what are the dimensions of the m here? The dimensions. The dimensions. The dimensions are for Q, what is the dimension? Meter cube per second means n to the power of 3, t to the power of minus 1. Yes or no? Meter cube means L cube. Area L square, velocity L by t means LT to the power of minus 1. Okay. L square and V is equals to L to the power of means LT equal to the power of minus 1. Okay. Now, if you see in this case here, now coming to the repeating variables, I told you one variable must be having a geometric variables and other must be having the kinematic variable. Okay. So now what is the geometric variable here? The geometric variable is, okay, so the whatever the geometric variable comes as a area. Whatever the geometric variable comes as a area. Now what about the kinematic variables, sir? What about the kinematic variable? The kinematic variable here is going to be velocity, because see, in the case of the area, what is the primary dimension? L. In the case of the kinematic, already I have taken L. Already I have taken L. Okay. Already I have taken L. So there is a T, and with respect to T, that is going to be the kinematic variable. Yes or no? And what about the fluid property, sir? Fluid variable or fluid property, this is going to be 0. Nothing is there. So how many number of repeating variables are there? Here is only 2. How many number of repeating variables here? The repeating variables is only 2, my dear. Okay. I hope you understood. And what are those? Those repeating variables are nothing but A into V. A and V. So those repeating variables are how many here? The repeating variables are only 2. Okay. So those are nothing but A and V. The repeating variables are A and V. Okay. And now the number of pi terms n minus m. Number of pi terms is equals to n minus m, which is equals to 3 minus 2 is equals to 1. Is equals to 3 minus 2 is equals to 1. And for further example, I'll give you one more example for you. Example 2. Time period of pendulum depends on length L and gravity G. Then what is the number of variables over here? Please tell me. Time period of the pendulum depends upon the length L and gravity is going to be G. Yes or no? Now I want a number of pi terms. So in this case, the time period is a function of L and G. So how many total number of variables are there? 3. Time, length and G. And see, I did not take the discharge over here, did I? No, because I shouldn't consider the Q, because this is a dependent variable. The dependent variable should not be taken as the repeating variable. So what are the repeating variables now? Here, In this case also, now you see here is going to be L and G. Now, what is the geometric variable? L. And what is the kinematic variable? G. This is a geometric variable L and kinetic variable is going to be G. And what is the M value here? 2. So pi terms are going to be 3 minus 2, which is going to be 1, because this represents geometry, this represents kinematic. So I hope you understood. So this is a small example, but I did not mention you. This is about just to find out the number of pi terms. That's it. Just to find out the number of pi terms. That's it. Now, after finding the number of pi terms, why we don't consider the dependent variable as repeating variable? That's the property given by the Buckingham. If you are taking the dependent also, or a dependent is dependent on some variables, and you are taking independent, and if you take dependent, then what is the meaning of that? Sir, how G is kinematic? What is G? Acceleration due to gravity now. That gravity means acceleration due to gravity. Okay. Acceleration due to gravity. Here, number of pi terms is equals to 3 minus 2. So, how many number of pi terms are there here also? 1. So now, yes, this chapter is similarly similar to you what you studied in physics in your intermediate. Okay. Now, let me go with the next point. So now, what is the procedure? So determining of, now once I know the number of pi terms, once I know the number of pi terms, so how we are going to design the number of pi terms or formation of the pi term? Formation of pi terms. So pi terms are going to be formed by combining m variables, by combining the m variables of the total number of variables. Out of the total number of variables, with the remaining variables are after you are going to repeating the n minus m. So with one of remaining n minus m variable, with one of remaining n minus m variable. So pi terms are formed by combining m variables out of the total n variable with one of the remaining n minus m variable. So what is the meaning of here, sir? Is how many number of pi terms are here? 1. So how many number of pi terms here? 1. Only pi 1. Pi 1 is equals to. So how I am going to repeat this one, sir? The repeating variables are going to be. So you are going to combine the repeating variable. What is the repeating variable over here? A and B. Yes, a to the power of a1, v to the power of b1. See, what I am doing over here is, observe this point clearly here, what I am mentioning. So, from here, the pi 1 value, how we are going to find is nothing but by combining the m variables. What are the m variables? What are the m variables? A and v. A power A, v power b. And with one of the remaining n minus 1 m variable. See, what is the remaining n minus m? Are Baba, m variables are a and v, and n variables are q, a, v. What is the remaining one of the remaining variable over here? Only Q, right? How many total variables are there? Q, A, V. Where A and V are the N minus M, means, A and V are the repeating variables. And what else remaining? The leftover is nothing but Q, right? Into Q. This is known as a pi term. This is known as a pi 1 term. And these M variables repeatedly used for the other remaining N minus M variables. So why we call this as repeating variables? Now let me take one big example, and from that you can see. Let me take the example. Give me a minute once. Yeah. So take that example. The resisting force, F of a ship, F of a ship is function of its length L, velocity V, length L, velocity V, acceleration due to gravity G. Now, so forget about the acceleration due to gravity here. Yeah, acceleration due to gravity G, and fluid properties like. So I'm taking an example, and from this example I'll explain you much more better. Fluid properties like density rho, viscosity as a mu. Write this relationship in a dimensionless form. Write this relationship in dimensionless form. Okay. Let's see how to find out this one. See, whatever the Q is equals to A, V, time, and R, those are the very, very small things. So now what we are going to do over here is, let's see. Listen to me. Solution. In the step number one, you first write down the total number of variables over here. You first write down the total number of variables. So what are the here? The variables are F, L, V, acceleration due to gravity G, density rho, and viscosity as a mu. F, L, V, G, rho, mu. Okay. Now you can see from here, where F is a function of, means force is a function of length, velocity, acceleration due to gravity, density of fluid, and viscosity of the fluid. Okay. Now you see how many total number of variables are there. The dependent is going to be F. What is N? N means dependent plus independent variables. So what is the dependent force plus what is the independent 5, 6. So what are the total number of variables are here? Number of variables are going to be 6. So first in the given system, you take the total number of variables. Okay. Now, once you know the total number of variables, what you do is you just take out that dimensions. Step number 2. Dimensions for all those things. Dimensions. So first of all, you know the units of the force. Yes. So what are the units of the force? Tell me. What are the units of the force? Mass into acceleration, kg meter per second square. Yes or no? For force units, first I will go with the units. And once I know the units, then I can find out the dimensions also. Units of the force. Force is mass into acceleration, kg meter per second square. Yes or no? Okay. Now, next, length in terms of meters. Okay. Velocity in terms of meter per second. Acceleration due to gravity, meter per second square. Then density, what is the density? Density means mass per unit volume or not? Meter cube. Sorry. Kg per meter cube. And what about the viscosity, sir? This is dynamic viscosity. The dynamic viscosity means kg per meter second. Kg per the meter second. Okay. So these are the units. These are the fundamental units of the given. And now you write down the dimensions for all those things. Now coming to the dimensions. In terms of dimensions, force is kg means mass, meter means L, S means time, t to the power of minus 2. And L means L only. And velocity, meter per second, L t to the power of minus 1. Acceleration due to gravity, meter per second square, t to the power of minus 2. Density, kg per meter cube, m L to the power of minus 3. Viscosity, kg m L to the power of minus 1, t to the power of minus 1. So these are the dimensions. Yes. So once I know the dimensions, now coming to the step 3. So step 1 is going to be this one. Step 2, dimensions. Next come to the step 3. Step 3 is selection of repeating variables. So how we are going to select the number of repeating variables is, now if you, the people who don't have understood the skew, AV and time, now you can observe here in this case. So how we are going to select the repeating variables? The selection of the repeating variables here, you are going to see first point, the dependent variable should not be considered as a repeating variable. Dependent variable should not be considered as a repeating variable. Okay. Now, point number 2. What are the geometric variables over here? The geometric variables are only length. Only length. Length is the only geometric variable. Yes or no? Only length. Length is the only geometric variable. And kinematic variable are wherever you see the time. Kinematic variable are here. Kinematic means velocity comes under kinematic and gravity also comes under the kinematic. Yes or no? And fluid property is fluid property. What are the fluid properties? Mass. Wherever mass is there, see first length. Once I write length, then I don't care about the length. I look over the time. So time means V and G. Now mass and mass, density and viscosity. Density and viscosity. Okay. Are sir, here there are two kinematic variables, two fluid properties and one geometry. Then how come I fix the repeating variables, sir? Sir, what is the meaning of repeating variables, sir? One variable must be having channel geometry, one variable must be having the kinematic, and one variable must be having the fluid property. Yes or no? Now come to the last point. What is the third point I mentioned? No two repeating variables has the same primary dimension, which means if I take a repeating variable with respect to geometry, only L should be there. And if I take with respect to kinematic, only one variable should be there. Here V and G, the primary dimension of the velocity and the gravity is a kinematic variable. But you know that no two repeating variables should not have same primary dimensions. So now what I do is, the M variables are, or the repeating variables are First, with respect to geometry, I am going to take it as a L, okay? And now, how many properties are there here? How many variables are there here? So here I have a, yeah, here in the case of the kinematics, how many are there? V and G, velocity and gravity. Velocity and gravity, both are kinematic, but no two repeating variables have same primary dimension. So can you take these two or only one? If I say time, only one repeating variable should be there. Now the question is, should I have to take R, V? Should I have to take V or G? When you come this type of now, you please observe what is the units of V and G? LT to the power of -1, LT to the power of -2. Which one is simpler out of these two? LT to the power of -1. The power is less. Whichever having lesser power or less dimension, you prefer that. V and G, now repeating the point again. So geometry I have already considered. Now other variable should be kinematic. So for the kinematic, only one should be there. You cannot take two. So how many variables in the given system is showing kinematics? Velocity and acceleration due to gravity. So now out of V and G, should I give preference for V or should I give preference for G? For the V, the power is only -1. For the G, the power is -2. We always goes with the simplicity. We always go with the simplicity, which means now what I do is I give preference for the V instead of G because the units of the V are much more less than the units of the G. Now here this is going to be the Array, what is the mu or not kinetic variable? Wow, mu is a property, viscosity is a property. Viscosity is the property. And now coming to the fluid property. Fluid property means a property of the fluid. Yes, that whenever I say the fluid property, the fluid must be having mass. So now the primary dimension is going to be mass, and mass is there in two terms. The mass is there in two terms. Yes, rho and mu. But should I have to take two variables having same primary dimension, or only one variable as a primary dimension? Only one. Now out of this rho and mu, you please tell me which one I have to take as a repeating variable. Now out of these two, here there is M, L, T. Here there is only M and L. So now which one is going to be simpler? Here only two primary dimensions are there. Here three are there. So for me, it is simple to go with the ML rather than the MLT. So the last one is going to be rho. Last one is going to be rho. So the M variables are L, V, rho. So total number of M variables is 3. Now I can write one point here as note point. The maximum number of repeating variables are primary dimensions. Primary dimensions 3. The maximum is going to be 3. So I hope you understood. No matter whatever they give, see, generally the most common geometry is L. The most common first kinematic variable is going to be V, and the most common fluid property is density. The most common, these are the most common repeating variables. But still I did not understand why you call it as a repeating variable, sir. Give me a minute, I have to bring some water. Please have a look. Okay. Yeah. Why density here? So in Python we consider dependent variable also. Now you see. So why density means in the case of the density only M and L. In the case of viscosity M, L, T. Which one is simpler? Arey Baba, you always go with if number of terms are there, that is simple. If power is less, that is also simple. Yes or no? So here my question is M power and here M power both are same. M powers are same, but the L and T you see, the T is extra over here. So the max number of real variables are going to be 3. Now, so step number 4. Step number 4. Number of items are n minus m. And what is this n minus m? N minus m are going to be 6 minus 3. 6 minus 3. Okay. So this is the number of items. How many items are there? 3 items are there, which means pi 1, pi 2, pi 3. Pi 1, pi 2, pi 3. Now what I am going to do here is the last step. So for formation of the items, how I am going to form the items? Items are going to be formed by combining the m variables out of the total n variables with one of the remaining variable each. With one of the remaining n minus m variable each. Now, what are the m variables over here? L, V, rho. So what I do is pi 1 is what are the repeating variables, please? The m variables L, V, rho. L to the power of A1, V to the power of B1, rho to the power of C1 into combined with what? Combined with the one of the remaining n minus m variable. So if they are going to be the 3, what are the remaining n of the n minus this? What are the remaining n minus m variables? 3 variables. What are the please? So total how many are there? 6. Now I am remaining L, V, rho. L, V, rho will be remained. What are the remaining things? F, G, mu. F, G, mu. These are the remaining variables or not? M variables are there. Apart from the M variables, whatever left over is M, F, G, mu. Now what I do is, I'll write down the items by combining these M variables with one of the remaining. With one means only F. Only F. So pi 1 with respect to F. Now pi 2 is same. Again you repeat. Now pi 2 term is combination of the m variables. What are the m variables? L to the power of 8 L, V, rho. But this time B2, C2, C means B2, C2. And now one of the other variable. What are the already F I used? Now this is going to be G. Similarly, pi 3 is equals to L to the power of A3, V to the power of P3, rho to the power of C3. Then the remaining is going to be mu. As m variables are using repeatedly to form items, they can say as repeating variables. So what are the variables that are repeating? Sir, why you are taking this power A1, B1, C1, sir? So what is the meaning of pi, sir? The meaning of the pi is dimensionless, right? What is the meaning of pi? What is the meaning of pi, first of all? The meaning of pi is dimensionless. So no dimensions should be there. No dimensions should be there. So whatever you take, the dimensions m to the power of 0, L to the power of t to the power of 0. So all these things should not consist of any dimensions. M naught, L naught, T. So step number 4 is, what I am doing is, I am combining the m variables with each time one of the remaining variables. With each time one of the remaining variables. So how to decide f g mu? You don't need to decide, Baba. You can say it as the first one should be depending variable, and the other things you can write as mu or you can write as g. So should I have to write pi 2 as g only? No, it's up to you. I'm not. There is no hard and soft rule. You can write pi 1 as g, pi 2 as f, pi 3 as mu. You can write pi 1 as mu, pi 2 as g, pi 3 as f. It's up to you. It's up to you. Now let's find out these powers. What is this terms? So first one, step 5, finding this pi 1, pi 2, pi 3. Okay, once I know this, then pi 1 is equals to L to the power of A1, V to the power of B1, rho to the power of C1 into F, and now its dimensions are going to be M, L, T to the power of 0. So what you need to do is you have to write down the dimensions. Already we have dimensions, right? So you have the dimensions. Please write down the dimensions of L. What is the dimensions of L, please? L means L to the power of V1 only, but V, L T to the power of minus 1 V1, rho kg per meter cube, M L to the power of minus 3 C1 into F. What is F? What is F, please? F means kg per meter square, sorry, meter per second square, ml t to the power of minus 2 must be equals to m to the power of 0, l to the power of 0, t to the power of 0. So just simply what I'm doing is, now I want to find out the pi 1 term. I want to find out the powers over here. So now let's take m terms on one side, means from here. What is m term? M power c1, here 1, c1 plus 1. C1 plus 1. And similarly, L. What is L over here? A1 plus L to the power of plus B1 minus 3C1 plus L1. Yes or no? I hope you are able to understand this. Then T to the power of here, there is no T, and here minus B1, here no T, minus 2 is equals to m to the power of 0, l to the power of 0, t to the power of 0. I hope you understood what I have done. In the case of the step 5, what I have done is just simply I am substituting the dimensions and making sure, because you know the meaning of dimension analysis is study of the dimensions. You know the meaning of the dimension analysis is study of the dimensions. Okay. Now, once you know this, then you please find out the C1 plus 1. So from LHS is equals to RHS. This is nothing but the dimensional homogeneity. So from here, I can write C1 plus 1 is equals to 0. So what is C1? Minus 1. Similarly, minus B1 minus B2 is equals to 0. B1 is equals to minus B2. So don't ask me, sir, why you are taking 0. Because you see, equate the powers. Now, what is your L power over here? The last one. A1 plus B1 minus 3C1 plus 1 is equals to 0. And you know that A1 is nothing but C1, sorry, A1 plus B1 minus 2 minus 3 into minus 1 plus 1 is equals to 0. So what is A1 value now? What is A1 value, please? So minus of minus plus 4 minus 2 plus 2, and if it goes to the other side, minus 2. So now I got to know the A1 value, B1 value, C1 value. So what is our pi 1 now? Pi 1 is nothing but L to the power of A1 means L to the power of minus 2, and V to the power of B1, V to the power of minus 2, and C to the power of, means what is the rho to the power of C1? C1 is nothing but minus 1 into F. And this pi 1 can I written as F by rho L square V square. That's it. F by rho L square V square. So similarly, see, I hope you understood the first one. I hope you understood the first one. Haven't you? Please observe what I have done. A1, B1, C1. So LHS is equals to RHS. And this, what are the dimensions over here? F by rho L square V square, which is nothing but ratio of the forces. In the case of the Reynolds number or Grafraud's number earlier, if you remember, the inertia force. What is inertia force? If you remember, I written as rho L square V square. You go back and you see that's nothing but inertia force. So F is a force and rho L square V square, that is nothing but inertia force. Yes or no? It's the ratio of the forces, my dear. It's the ratio of the forces. Okay. So any doubt with this? Just tell me. It's a time taking only. It's time taking only. Step 5 not understood. Are Baba, you just substitute the dimensions, right? Substitute the dimension of V, dimension of rho, and that is going to be m to the power of 0, L to the power of 0, T to the power of 0. Now similarly, what is pi 2? Pi 2, L to the power of A2, V to the power of B2, rho to the power of C2 into G. If you solve, then what you are going to get is you are going to end up the A2 values as, okay, so A2 is equals to 1, B2 is equals to -2, C2 is equals to 0. You solve this, I am not going to solve it. Then pi 2 is equals to L V to the power of -2, rho to the power of 0 into G. So pi 2 is equals to G by GL by V square. Pi 2 is equals to GL by V square. Similarly, you find out pi 3. Yeah. Is it important for the gate? Yes, they may ask the question. So for every 2 to 3 years, they're asking one question from the dimension analysis. Actually, this part is lengthy, but we must have to decide. We must have to look over this one. So in examination, they may not give these many conditions like step 1, step. See, once you understand the topic now, then you can go through this. I am giving you elaborate solution. I am giving you the elaborate solution. It's as a steps wise. So if you understand this question, you can solve the remaining questions. In examination, especially gate point of view and ESC prelims, they'll ask a question as just how many number of items are there. They won't ask you develop the items also. They won't ask you to develop the items also, but we need to know the entire concept here. So now what is pi 3? L to the power of A3, V to the power of B3, rho to the power of C3 into what is remaining here? So what is remaining? The remaining is going to be mu. Now if you solve for this, the A value is going to be -1, B3 value is going to be -1, C3 is also going to be -1. So once you know this, then pi 3 is equals to L to the power of -1, B to the power of -1. Yes. Rho to the power of -1 into mu. So pi 3 is equals to mu by rho VL. So here pi 2, here pi 3, and this is going to be the pi 1. Once I know the pi 1, then the relation between here is, sir, how ABC value is decided, sir? Arey, do you have any brains with you? After all this, you are asking me how the ABC values are going to be decided. Arey, kya re bhai? I don't know whether you are following or not, or you are in some trance. I'm telling you, you write down in terms of the dimensions, and once you write this, the powers you are there, right? These powers you equate it to m to the power of 0, L to the power of 0, T to the power of 0. And once you know that, From here, how I find out C1 here? How I find out B1? How I find out A1? Similarly, you write the dimensions for these two. Pi 2 and pi 3. You will get pi 2 and you can pi 3. You please try it in your home. Then you can understand much more better. So now, after all, now the relation between pi terms is pi 1 is a function of, now pi 1 is a function of pi 2, pi 3 and so on. So what is the pi 1 here? The pi 1 is nothing but f by rho L square V square is a function of, what is pi 2? GL by V square. And what is pi 3? Mu by rho VL. You see, can I write FR square? You know, FR is nothing but V by root GL and Reynolds number rho VL by mu. Yes or no? Froude number is V by root GL, where L is D in open channel flow. Reynolds number is rho VL by mu. Now, can I write this one as further? F by rho L square V square is a function of 1 by FR square 1 by Reynolds number. This is the relation. This is the relation. I started with this. Now, what is the relation between the dimension? I'm asking you, write the relation in dimensionless form. So these are all the dimensionless. Froude number does not have any dimension. Reynolds number does not have any dimension. And this force ratio does not have any dimension. But this is the relation between the dimensionless terms. I took 6 variables and I ended with 3 variables. How many variables I have started? I have started with the 6 variables. Now final answer is consists of only 3 variables. If you know the total number of variables, how to get down the relation between those variables in terms of dimensionless groups. This is okay. Please have a look. So the main important terms are apart from this, the most viscosity is there. Apart from this, if, for example, if they give kinematic viscosity, the kinematic viscosity are meter square per second. So these are the main things only, and apart from this, there is no much you required. So the main things is going to be this one. This is kinematic viscosity, mu. And this one is going to be dynamic viscosity, mu and nu. Okay, so that's all with this. This is about the method of, we can expect this question conventional part. IES mains, you can get this one. But in this chapter, the most important part is yet to come. That is known as model tests and model studies. So today, whatever the discussion I made is about the dimensions, methods of the dimension analysis. So what are the objectives of the DA, dimensional homogeneity, and what are the methods? So in this, in examination, gate examination, they'll ask how to find out the number of pi terms only. They won't ask about the formation of the pi terms. They won't ask about formation of pi terms. So, you know, you go through this example, everything I have written clearly. So finally. No, is this chapter completed? No, it's not completed. The last objective, what is the last objective? The last objective, this is very important that we'll be discussing tomorrow. So tomorrow we'll see the remaining things, and by tomorrow dimension analysis will be completed, and I'll take the doubt clearing section tomorrow because I don't know, my throat is paining. So even I have one more class at 11 o'clock onwards. So I'll take the doubt clearing session definitely, but not today. So it will be 10 o'clock, right? Send PDF as early as possible. See, I'm having a class up to 6:30. One more online class is there for me from the next 11 o'clock to evening 6:30. So that's going to be a 6 to 7 hours journey, and I don't get a time in between. I get a time for the lunch or some 15 minutes break only. So that's the reason why I'm sending you the PDF at 7 o'clock. Okay, I hope you understood that. Okay, fine. That's remaining things now. I'll see you tomorrow. But as of now, for today, I'll take a leave. We'll meet tomorrow morning. Yes, okay, fine. Same time tomorrow. And tomorrow we'll complete the syllabus for the gate. Tomorrow is the last day for the gate people. And for the IES, 2 more days would be there, flow measurement devices, so that we'll be discussing. So today is a Thursday, right? Thursday or Friday? Yeah, today is Thursday. So tomorrow, Friday, we'll complete the syllabus for the gate. Saturday, Sunday, by Sunday, we'll be completing the IES also. Okay. So we have a good day.